Now section 5.3, we don't, strictly speaking, have any new maths here, but because this is where a lot of the tricky sort of questions come in and where people sometimes get stuck, this is, I thought it was worth putting a video together anyway. It starts slightly oddly by reminding us of some formulas that we've known for a long time. Now the reason that it's worth reminding us of the formula for a volume of a cylinder or a volume of a cone is this. A very typical question is the one that we've got in example 3. We've got a curve, x-axis, y-axis. Now the curve is given by y equals x cubed plus 2. And then we've got a line given by y equals 5 minus 2x. And what we're being asked to do is take this region here and rotate it around the x-axis. So we can picture that volume of revolution. Now, first of all, this point here, the x value is obviously 0, that's the y-axis. This point here, I need to know the x value, and this point here, I need to know the x value. And I'll explain why if that's not obvious, I'll explain in just a moment. So what's the x value of this point here? Well, this is the point where the line and the curve cross. So if we just solve the line and the curve simultaneously, that should give us the point where these things cross. Now, hopefully by the point you've got to this chapter in the course, that's completely automatic. Where do two functions cross? Well, solve the equation simultaneously, and that will tell you the x and y axis of the crossing points. They do that for us in the example, and we come out with the x value of 1. Where does this line cross the x-axis? And again, hopefully this is completely automatic. Y equals 0, that tells you where it crosses the x-axis. So put y equal to 0 in here, take away 5, divide by minus 2, so this is 5 over 2, okay? Now, this one, if I want to find the volume of revolution for this bit here, what happens when I rotate this around the x-axis? That's the integral from 0 to 1 of y squared, which is x cubed plus 2, don't forget to square it, oops, with respect to x, times by pi, no problem. This area here, I'm going to rotate that about the y-axis as well. Now, one way of doing that would be just to say, well, this area here is given by pi times the integral from 1 to 5 over 2 of 5 minus 2x all squared with respect to x. And that's fine. That's true. That will work. But think about it. If this is a triangle, if I rotate that around the y-axis, I'll draw a separate diagram, so hopefully it'll be a little bit clearer. But what am I going to get? The shape that I'm going to get, well, it really doesn't look very clear, but hopefully you can picture the shape you're going to get is a cone, isn't it? Okay? If you take a triangle and you rotate it around, the shape that you're making is just a cone. The more times I try and draw this, the less it seems to look like a cone, but hopefully you can see that, hopefully you can picture it. If I take a triangle and rotate it around, if I take a right angle triangle and rotate it, then I'm going to get a cone. Now, that cone has obviously been taken and sort of stuck on its side, but it's a cone nevertheless. Now, you could do this integral, that would be fine, but it might be easier to think of that as a cone, and the volume of a cone is 1/3 times pi r squared h. Well, the radius of the cone is the distance from here to here. Well, we know that distance because it is the y-coordinate of the crossing points, and we found that in part A was 3. So that is going to be 1/3. So this bit here is equal to pi times r squared times h. So that's pi, 1/3 times pi times r squared. Well, that y-axis there is, that y-coordinate there is a 3. So 3 squared times h, which is this distance here, which is, well, from 1 to 5 over 2 is 1.5, okay? Now, that is obviously an easier calculation than having to do this whole integral, so it's helpful to know that. Similarly, if you have an example, something like this, we got a function and then a horizontal line, and they want us to find the area, the volume of revolution of that bit and this bit. Well, when I take a horizontal line and rotate it around the x-axis, what I'm going to get is going to be a cylinder, isn't it? So if you've got a horizontal line and you rotate that around the x-axis, you're going to get a cylinder. If you've got a diagonal line, you know, a non-horizontal line, and you rotate that around the x-axis, you're going to get a cube. So it's helpful to have those volumes just as formulas, because that will probably make life easier. The other situation that we can have is where we don't have nice functions like straight lines. We've got two curves, and we want to find what happens if we, I'm just trying to copy roughly what happens in example 4 here, so I've drawn the curves about the same shape. If I need to find the volume that I get when I rotate this bit around the x-axis. Now, I think probably the most straightforward way to do this is the way that they're recommending in the book, which is to take this whole area. So this is, let's call this function f1. I'm diverging now slightly from the example 4. I'm just going to call this f1 and f2. So they could be any old functions, right? Well, I can integrate pi times f1 of x squared with respect to x. So whatever f1 is, in this case I think it happens to be square root of x. So take square root of x, square it, and integrate from a to b. And that will tell me the volume of revolution that I get when I take this red shaded area and I rotate it around the y-axis. If I then take away this area under here, then I'm going to get, if I take away the volume created by this area under here, which is pi times the integral from a to b of f of 2 squared with respect to x, then I'm going to get the volume created by rotating this area around the x-axis. Okay. Now the easiest thing to do is probably that. Find that integral, find this integral, take one volume away from the other, in the same sort of way as we would if we were finding areas. Now on the other hand though, if we look at this, there's a pi here and there's a pi here, so I can take the pi out the front. I'm integrating from a to b here and I'm integrating from a to b here, so I could give myself this formula. So I could square this function, I could square this function, and I could do this one squared, take away this one squared, and then I can integrate from a to b and times by pi, and that would be the same thing. Now, the reason that that's a problem is that it's very easy to mix up the top function and the bottom function and end up doing the take away the wrong way round. It's very easy to mess up in the algebra when you're doing this squared, take away this squared, and ultimately, probably doing this squared and then taking away this squared, you're not going to end up with a simpler function anyway. You're just going to have to integrate this one and then integrate this one and sort of do those separately. So although this is true, it's not incredibly helpful. It will save you a little bit of algebra perhaps, but the effort that it saves you in algebra is compensated for by the fact that it's actually a bit fiddlier to do. So overall it comes out about the same. The other thing to watch out for is that if you do it as picturing the whole volume, take away the smaller volume, you've just got a better idea of what's going on in your head. You can work out a smaller part of the question at once. So it's up to you. Some people prefer to go for this way. Some people prefer to go for picturing what's going on. I would recommend sticking with the method that they have in example 4 on page 80, which is the bigger volume, take away the smaller volume. In section 5.4, there's not much more to add. By this point in the course, depending on what order you're doing these books in, but I think you'll be used to these modelling sections by now. The idea is that the exam board are very keen on students applying questions and putting questions in context, and so they've put an extra section at the end of the chapter about modelling. There isn't really much more to say. It is just questions in context. You could do all of these questions on the back of what we've done in section 5.1, 2 and 3, but because they're important, they've made a whole extra exercise out of it to make sure that you're practicing these things carefully. That's not to say that they're easy questions. It's just to say that there is no new maths to tell you about here. You need to read the information that you've got, realise that the way to solve that is a volume of revolution, and then you use the volume of revolution mathematics to get there. Okay, there's nothing more that I can tell you. There's nothing. There isn't anything sneaky. Sometimes these modelling sections link with mechanics or statistics, and sometimes there's a particular kind of question that comes up a lot. But here, it is just a case of read the context of the question you've got. Once you've realised it's a volume of revolution question, then hopefully you can work out which bit of the mathematics from section 5.1, 2 and 3 you need to use. So that is chapter 5. Good luck with all that.